Okay, we're obviously going to need the Laplace transform of delta of t. Everything we're doing is essentially based on the Laplace transform. So let's just compute it. So what's the Laplace transform of delta t? We won't typically write capital delta of s, and you'll see that that's because the Laplace transform of the unit impulse is particularly simple. How do we get it? Well, let's take the unilateral transform, and it's because of essentially this unit impulse function that we use as our lower limit of integration for the unilateral transform 0 minus. We can't actually start right at 0 because we want to be able to integrate over the 0 width, if you like, of this unit impulse function. Okay, so by definition, the unilateral transform, that upper limit of integration should be infinity. We just need to take the transform of delta of t times e to the minus st dt. But the value of this integral follows directly from our sifting property. In this case, the f of t that appears in the definition of the sifting property is just e to the minus st. We could write it in terms of tau to make things clearer. Okay, so this is really an instance of the sifting property. Our f of t, or f of tau rather, is e to the minus s tau. And our delta of t minus tau is just delta of tau. So in other words, this is an instance of the sifting property where f of tau is e to the minus s tau and little t is 0. So by the sifting property, the value of this integral is just going to be our function f, in other words, e to the minus s tau, evaluated when tau equals t, which in this case is 0. So the integral is simply equal to 1 by the sifting property of the unit impulse function. In other words, the Laplace transform of the unit impulse is 1. So if you're ever having to invert a Laplace transform, and the partial fractions expansion has a constant term, that means that your function involves an impulse like this. So this is in addition to our table of Laplace transforms, and in fact this is included in the table that you've already been given. Okay, let's just go back to the notion that we began this week's lectures with, namely the notion of the zero state response and the zero input response. And in particular, let's consider the zero state response. And we'll just use our example of the mass spring damper. So in that case, we have this function 1 over ms squared plus bs plus k times f of s, where f of s is our input, or our forcing function. So if our forcing function actually has the form of a unit impulse, what do we get? Well, in that case, its transform, f of s, is just equal to 1. So y of s equals 1 over ms squared plus bs plus k itself. So we said that we're going to call this function that multiplies the transform of the input in our zero state response, the transfer function. And we'll be talking a lot about transfer functions in the future. But what is this transfer function? Well, we've just seen that the transfer function is the sort of zero state response to an input that is the form of a unit impulse. We call it, if you like, the transform of the impulse response of the system. So if all of the initial conditions are zero and our input or forcing function takes the form of a unit impulse, the response that we get is what we call the impulse response. And its transform is this transfer function. That obviously plays an important role in determining the zero state response. So this, in fact, is going to be our main model of dynamic systems in the systems and signals part of the course. We'll be using this equation a lot that says that the transform of the output is equal to the transfer function times the transform of the input. And one of the significances of this transfer function is that it is the Laplace transform of the impulse response. This will lead immediately to a really key property of the so-called linear time invariant systems that we're going to look at. If you recall the properties of the Laplace transform, in this case we're doing a multiplication of the transfer function by the transform of the input in the S domain. And what we saw is that multiplication in the S domain corresponds to convolution in the time domain. So in fact, the zero state response of a so-called linear time invariant system in the time domain is the convolution of the input with the impulse response. So by the convolution property, of the Laplace transform, the zero state response of what we call a linear time invariant system, and we'll of course define exactly what we mean by this, is the convolution of the input to the system with the system's impulse response. This is a very fundamental result on these so-called linear time invariant systems, which are the ones we're going to be studying. And it follows from the fact that the transform of the unit impulse is 1, and from the fact that the transform of the zero state response is the product of the transfer function and the transform of the input. So if the input is a unit impulse, this transform f of s is 1, which means that y of s is equal to this transfer function. Therefore, this transfer function is simply the transform of the response of the system to an impulse function, a unit impulse function, when its initial conditions are all 0. So we're going to go over all of this. What's a linear time invariant system? What is its impulse response and its transfer function later on? This is just a quick preview of some of the things that follow immediately from our definition of the unit impulse function and from the fact that its transform is equal to 1. And that concludes this week's lectures.